Everyone. Thank you for being here. So this is, we'll continue our sessions on FHE. So we have several dedicated sessions on FHE in this year's CHES conference, and this one is on bootstrapping. So our first paper is on a fast heuristic for mapping Boolean circuits to functional bootstrapping, and our presenter is Sergio Karpov.
Thank you. So yeah, I'll I'll start with an introduction of HE, but I think it's third time in this morning you've heard it. So yeah, I'll go on high level. So fully homomorphic encryption is a crypto system where you can perform computations of encrypted data, encrypted messages, and you have noise in the ciphertext for security reasons, and you lose the message if the noise overlaps. So you are limited in the number of computations you can do. So in order to avoid this, there's a bootstrapping procedure which will decrease the noise in the ciphertext to a level where you can continue the computations. So you do computations, you bootstrap, you do computations, you bootstrap. There are two designs, so two flavors of homomorphic encryption schemes. The first one proposed were schemes where bootstrapping is costly, but you can encrypt, you can encode several thousands of messages in a ciphertext. So you do like some kind of SAMD. And the second flavor is the FU or TFHE, where it's a bootstrapping scheme where it's a homomorphic encryption scheme where bootstrapping is fast, and but you can only increase a single message per ciphertext, and you bootstrap after each operation. So you bootstrap as often as you can. And in addition to lowering the noise in the ciphertext, the bootstrapping procedure can evaluate arbitrary functions. There are two main schemes. The first one proposed as a FU scheme, and the second one is a TFHE. All they look into evaluating Boolean gates. So now, what's the functional bootstrapping? It's you can call it programmable bootstrapping by different schools for this, and you can evaluate a function from ZP to ZP, an arbitrary function from ZP to ZP, in addition to lowering ciphertext node. And the computational cost of functional bootstrapping mainly depends on the precision of your plain text space. So high precision means a high cost. So here, yeah, for example, the execution time in TF-HERS from Zama as a function of bootstrapping precision of ZP, it's increasing non-linearly. So it's always better to have a lower P message space, but you'll lose in the functionality. So there are two things which you'll use in this work. The first one is non-power of two functional bootstrappings, because functional bootstrapping support any plain text space. Usually in the implementations we limit to power of 2s because it's the analysis, noise analysis is simpler. And if we use a non-power of 2 plain text space, the noise increase is slightly worse because plain text space is not a divider of ring dimension. And the second usable property of functional bootstrapping we'll use is the neg-cyclic functional bootstrapping, which in addition to evaluating any function from ZP to ZP, we can evaluate a neg-cyclic function from 2 times larger input plain text space. But the only condition is that your function must verify this expression. So it's a function which changes the sign over the second half of your plaintext space. And this property is due to the fact that we use an acyclic polynomial ring in, in implementations like TFHE. So the functional bootstrapping is limited to one input functions. In order to transform it to multi-input functions, what we do is we evaluate linear combinations of inputs. So we combine LW ciphertexts using linear combination phi. And after, when we have one single value, we evaluate a functional bootstrapping, a single functional bootstrapping. So in this way, you can evaluate any function from any n variable functions, any n variable function using the single value functional bootstrapping. A linear combination phi is valid for a function f if it can unambiguously distinguish its image. So for each 2x where the function that where the function you want to evaluate doesn't have the same value, the linear combination must have different values also. So in this way, you are sure that you can distinguish the input function values. So we'll use a notion in the paper, which is the linear combination size, because once you evaluate the linear combination, you must not overlap of the plaintext space you have in the functional bootstrapping. Otherwise, you lose. So given a function f, you can find a linear combination, an optimal one, but it's the exact methods are untractable. And what you can do is use heuristics. But in any case, the heuristics are they all depends on the execution time will be exponential in the number of variable inputs. For example, you can have linear combinations which, as a function of a function you want to evaluate using 2 times the same word. You can evaluate symmetric Boolean functions with a functional bootstrapping of size p. And in this case, if a function is symmetric, you'll be able to evaluate an input Boolean function, an input symmetric Boolean function with a functional bootstrapping of size n. And there are a lot of symmetric Boolean functions in practice, like the AND, the OR, the majority functions. And also, if you want to evaluate an arbitrary Boolean function, what you can use is base 2 composition or linear combination. This one. So in this linear combination is functionally complete, so we can evaluate any Boolean function with this one. But the drawback is size. It's exponential in the number of inputs. So you'll have to use a bootstrapping space of size 2 to the power of n for an input Boolean function. So which gives an expensive multi-input functional bootstrapping. What will be nice is to have, for sure, in there are functions which are between these 2 categories. So it will be nice to use these properties of a function we evaluate in order to be somewhere between these 2 cases. So let's dive into the problem we want to study to solve. So we are given a Boolean circuit, and we want to map it to functional bootstrapping, to evaluate it using a fast bootstrapping scheme. So to do this, we need to partition the circuit into subgraphs and to map each subgraph to a functional bootstrapping. And besides, we require that for each subgraph, for each partition of a circuit, we find a valid linear combination which can evaluate, which combined in a functional bootstrapping can evaluate this subcircuit. So our objective will be to minimize the number of functional bootstrapping in the map circuit, and which ideally should also minimize the execution time. Less bootstrapping, less execution time. Strange. So there are some, there are a lot of, there are not so many, but there are some related works which want to do the same. The first ones are inspired from the logic synthesis domain, and they are using power of two plain text spaces, which reduces the benefits or the possibilities to the bootstrapping. Also, the drawback is that they are searching for linear combination for an input functions, which is resource intensive. Then there are another works which do the mapping to functional bootstrapping manually. For example, for cryptographic algorithms used in transciphering. They use, because they're doing this manually, you can you know all the tricks you can use in the scheme to increase the efficiency, like negative cyclicity. You can increase the plain text spaces, etc. The drawbacks of manual mapping is these methods are difficult and time-consuming, and as we'll see later, it's you don't always find the best solution. So to solve this mapping problem, we're proposing a fast heuristic method, in which we take an input as a Boolean circuit to two input gates, and maximal functional bootstrapping precision. So that's we are fixing this bootstrapping precision. We don't want to overflow it. And the main idea of a heuristics is quite simple. We traverse the circuit gates in topological order. We traverse them once, and we construct a linear combination of a gate on the fly from the linear combinations of its inputs. So we combine the input linear combinations into a larger one, and if a linear combination of a gate we are looking into at the moment is too large, we try to eagerly bootstrap one of the inputs of a gate, and we do this with second input if we cannot map to a given precision function bootstrapping precision. So let me give you an example of how this heuristic works to ease the presentation. Suppose you have this circuit which has 3 inputs and 2 gates, and XOR gate and an AND gate. So the first step will assign to each input 2 tables. One is the truth table of input, which is either can be 0 or 1. And the second one is, we call it a multivariate table, which is the evaluation of linear combination of this subgraph or this of a cone, of a circuit cone which ends in this node. So for inputs, it's 0, 1 in all cases. The next step will we'll look into the XOR gate because it's the next one to the topological order, and we'll compute the truth table of the XOR gate by doing the product of the truth tables of its inputs and computing the evaluating these truth tables using a function XOR. So it's 0, 1, 1. 0, 1, 1, 0. And we do the same thing for the multi-value table. We do the canonical product of the table, two inputs tables. And we combine them using the coefficients of a linear combination. We'll speak later how do we find these combinations. But for now, suppose that someone gives them. So when you do this, you'll be able to, when you do the linear combination of inputs, you'll obtain 0, 1, 1, 2, which is a valid linear combination for this gate because it allows to distinguish the truth table of this gate. So we do this for the next gate, and in this case we'll find linear combination. It's A plus B plus 2C because this is a valid linear combination for the subcircuit which ends in this gate, in the AND gate. And because we want to output this node, if you output it directly, we'll output a value vector from 0 to 4, so a multi-value, and we simply bootstrap it. We perform functional bootstrapping on this value, on this linear combination. With a test vector, we compute from the truth table and the multi-value table, and we can output the Boolean value of the output. Yeah. Here it's the way we construct the test vector. It's not so important. Yes, and once we have bootstrapped this gate, we can reuse the bootstrap value, which is smaller. So we use the bootstrap. If we have other gates afterwards, we use this value. So we have 0, 1, 0, 1, and we continue the heuristics to till all the gates of circuits traversed visited. So the heuristic is fast because we visit the nodes only once, and we only build the linear combination incrementally. So we examine only two input linear combination at once. For the linear combination, we use an exhaustive search, and we try all the possible values in a given range, and we keep the value which gives the lowest size. Let's keep this example. We go to the implementation details. We've implemented it a proof of concept in Python. We use the concrete to estimate the function bootstrapping costs. We've patched it to support non-power 2s, plain text spaces. We use different Boolean circuit benchmarks, and we compare the map circuit to the circuit which is evaluated using gate bootstrapping. For iOS, we can see the two lines here. The number of bootstrap as a function of function bootstrapping size we are given, and in red is the evaluation time. The heuristic, when we increase the function bootstrapping size, the number of bootstraps decreases. But the evaluation time at a certain point begins to increase because the decrease in the number of bootstrappings is not sufficient to decrease the execution time of the overall circuit. We've tested the benchmark on APFL combinational benchmark suite. And overall, in average, we decrease the cost of evaluation by 37% compared to non-mapped circuits. And by the number of bootstraps, the decrease is almost by 60%. So now, yeah, we've tested the heuristic on Trivium and Crivium stream ciphers. And we compare them to hand-optimized versions from both 2023. So on Trivium, with the same solution as in the state of art, is the heuristic finds the same solution as the state of art. In red is the result proposed in both 2023. Our heuristic finds the same value, same number of bootstrapping, the same evaluation time. And besides, we can even found a solution with the same number of bootstraps, but with a functional bootstrapping size of size 3, which in practice gives us a slightly better execution evaluation time. For Crivium, things are better for the heuristic. The result from the boss is for Crivium they found, and I think it should be 10, yeah. 10 bootstraps for a functional bootstrapping size of 4. And our heuristic found a solution which with 8 bootstraps only, which in reality gives, which in evaluation time gives you a much better evaluation time, which is almost 50% faster than the 10 bootstrap solution. So final notes. The heuristic principle where you merge incrementally the gates is, even if it's simple, it yields very good results. Negasig and no power of 2 ciphertext spaces should be used because it allows to have more flexibility and to obtain better solutions. And in perspective, we want to execute the map circuit using not only estimating the evaluation time, but executing it to have more precise benchmarks results. And the same principle of heuristic can be applied to other privacy-preserving computation methods like the arithmetic Galbraith circuits. So this concludes my talk. Do you have some questions?
I think we have time for a couple of questions.
So I want to ask about scalability. So you mentioned in the last slide garbled circuits, and my understanding is that you've got to encrypt the truth table, right? So as you start to get to larger examples, that's not really feasible. Or am I missing something here?
I didn't follow you. What?
If the truth table has n equals 2 bits, that's 4 rows. I understand you can encrypt everything of the truth table that's small. If you have an actual practical circuit that does real calculations with 64 bits, you're not going to encrypt a truth table the size of 2 to the power of 64.
Yeah.
So
but
I was asking about scalability.
Yeah, for sure, because here we try to partition the circuit in the smaller, in partitions, and where each partition can be executed with a small truth table. So for example, 2 input, 3 input, 4 input truth table. but the circuit can be a 64-bit input circuit. It's no problem because you won't have a single lookup table for the 64-bit input circuit, but you'll have a number of smaller truth type tables.
Thank you.
Thank you for the nice talk. If you go to slide 23 or 24, you can see that in some of the, if you increase the FPS size, you still get a higher number of bootstrapping. But these PBSs or FBSs are more potent because they consist of more bits in it themselves already. Can you give some insight of where this is coming from?
Because it's the heuristic greediness. Because when you have a large plaintext space size, the heuristic will it's a greedy heuristic, so it will try to bootstrap later the inputs. So this can make decisions which are worse. Because if you, for example, suppose you have an input which has a large fan-out, a gate which has a large fan-out, and if the bootstrapping space is bigger, suppose that this input won't be bootstrapped, but all the outputs of this gate will need to be bootstrapped in the next level. So when you use a small functional bootstrapping size, the heuristic will bootstrap this gate, and all the other gates won't need to be bootstrapped. So in this way, you have this you have these spikes in the heuristic execution, even our bootstraps of the heuristic execution. It's because of a greediness. So,
thank you.
Okay.
Okay, let's thank Sergio for the nice presentation.
Thank you.
I request the next speaker to please come to the stage. So our next presentation is Velo FHE, GPU acceleration for Few and TFHE bootstrapping. And our presenter is Hao Yang. Over to you.
Okay, thanks for the introduction. And I'm Hao from City University of Hong Kong. And our paper is called Velo FHE, which is GPU acceleration for FHEW and TFHE bootstrapping. And so the talk will be divided into several parts. And first, I will introduce some background about like the differences between different types of FHE schemes and the motivation of this work. And secondly, I will dive into the key ideas and key design of our Velo FHE. And then I will talk about the details implementation. And then I would give a evaluation result and do a conclusion. And so let's begin. Let me introduce some background knowledge. And for the like 10 years, the recent 10 years, we are all talking about the choice of worldwide scheme or bitwise scheme. So let's do some comparison. So I think the first difference is their data packing technique, and for worldwide scheme, they usually are capable of packing a vector of data in using SIMD style and into slots. So for bitwise scheme, this is implicit because it can only encode a few bits. So for a large number, like a 64 integer, so for bitwise scheme, we should manually divide them into slices and do manual encoding. And I think the second difference is their ability of calculation, because for worldwide schemes they are able to do all types of linear functions, because they have the basic operation of addition and multiplication. Also some functional functions like rotation or automorphism. But for bitwise schemes, they can only do non-polynomial functions natively. But for in fact, all these schemes can do any type of computation with some complex construction. Yeah, but it may lose precision during the computation. So there is no perfect scheme for applications. So basically for this work, we focus on bitwise schemes, especially FHEW and TFHE, because we have a previous work on worldwide schemes called Phantom FHE. And for the motivation of our for this work, I think I would like to use 3 questions and try to explain these questions to give you the motivation. So the first question is why target bootstrapping? And for bitwise schemes, bootstrapping is the key operation, because each computation over ciphertext is done by doing a bootstrapping. So it's different from worldwide schemes, because they only need to do bootstrapping if the noise budget is low and they need to refresh. Okay, so for LW ciphertext, when we are doing a functional bootstrapping, it includes several steps or several modules, or several functions. So the first part is, the first task is blind rotation, and this is also the main function inside the bootstrapping. And then we will do a sample extraction, and also LW mode switch, also LW key switch. So I haven't done yet. So the bootstrapping is the cost mostly of the time consumption. So we target bootstrapping mostly because other parts are rather fast. So also not very suitable for GPU acceleration. And the bootstrapping part is time costing and also very suitable for GPU acceleration. Okay. So the next question is why use GPU on the accelerator as the accelerator? So in fact, we can use all type of accelerators, including GPU or FPGA or ASIC. I think it's all very suitable. Yeah, and why not just use CPU? Because I think CPU only have multi-threads, but the acceleration rate will be rather low than hardware accelerators. And I think GPU's SIMT architecture is also very suitable for accelerating like linear operations or the polynomial operations. Yeah, so we choose GPU for the accelerator. You can see in the figure that it's an overview of GPU architecture, and it consists of many streaming multiprocessors, which is very useful to do all types of calculations, including both floating point operations and also integer operations. Okay, the third question is what is the real bottleneck? So this is a complex question. So I will use some figures to explain more. And I think there is not only one bottleneck, but several bottlenecks. So we can talk about the first bottleneck is that we have a lot of tasks to assign to GPU. So basically, we need to do task scheduling manually in our code. And secondly, we have so it's very complex because it's not like CPU. So you cannot just port the code to GPU. You need to figure out what task is suitable for GPU and is friendly for GPU. And the second bottleneck is communication between CPU host memory and GPU device memory, because GPU is connected with CPU via PCIe, so it's not the highest transfer speed. So we need to take care of the data transmitted. And thirdly, it's inside the computation. So it's inside GPU SM. We need to try to optimize the arithmetic operations for FHE. And it's quite different from CPU because it has some different architecture design compared to CPU. And fourthly, we need to take care of the data access because inside the GPU memory, because each time we launch a GPU kernel, for this case we use NVIDIA GPU, so we can call it a CUDA kernel. So each time we launch a CUDA kernel, we need to first access some memory, load some memory from global memory to shared memory. So that costs a lot because both the ciphertext and the keys are rather large. So it's time consuming too. And also, according to the memory type, it may cause some access conflict. So it will lower the time. It will cost more time if the access pattern is not very good. And I will talk about the key contributions of our work. So let me show this pseudocode first, and this is the key steps. The key steps of the blind rotation. So we mainly focus on optimize this function. And in step 2, I just made say something wrong. So this is a host algorithm of the bootstrapping. So basically, the step 2 is the blind rotation I just mentioned. It's most time consuming because inside blind rotation there is a lot of steps inside. Yeah, and for this function, we have two optimization. First is we designed and we adapted and optimized the hybrid 4-step NTT tailored for GPU because in fact there were several 4-step NTT implementations already, both in mostly in hardware design. Yeah, so I will explain more what is this method like. And secondly, we modified to get a more compact blind rotation. So I will expand more to the two contributions. Okay, so thirdly, for step 5, in this function, we have some dimension-aware design to further optimize the key switch, and for the whole. And in the whole, we have we design designed a generic framework to implement both FHW and TFHE. Also, we support both the binary distribution, key distribution, and ternary key distribution of TFHE in our framework. So and also the framework, it can be easily extended into other like TFHE variants or FHW variants. Yeah, and our framework support batching of ciphertext computation. Also, we support multi-streaming, and we have workload partition for like assign some low computational task to CPU asynchronously. Okay, let's talk about the hybrid entity method I just mentioned. So this is the four steps of this entity variant. So in case if you are not familiar with this method, so I will expand a little more. So for a large n, we can use use n1 and n2, and n1 times n2 is the original n. And if we reduce the dimension of n, so we can we create 4 steps, and it seems to make the algorithm more complex, but actually it costs less than the original implementation because it's very friendly for hardware and also for GPU. So step 1 and step 4, we do a smaller degree entity, and for step 2 we need to multiply with a matrix consists of 2 factors, and for step 3 we will do a matrix transpose. Yeah, and in our method we use next cyclic convolution in step 1 and use cyclic convolution in step 4. And in our implementation, we have done a lot of optimization with regard to the memory access pattern. So we actually implemented an implicit matrix transposition, and that without conflict. And for the blind rotation, we applied the module tracing technique from the previous paper, and compared to gadget decomposition, compared to the traditional gadget decomposition, it can achieve a more compact implementation in the blind rotation So, but it's not all the case for all parameter sets. So we just use module tracing for several customized parameter sets. And we also modified this module tracing technique to get a more reduced noise growth during the computation. So for the key switching part, we do a dimension-aware adjustment to solve the input-output mismatch problem, and it's asynchronous between CPU and GPU to mitigate the workload imbalance problem. And for the whole framework design, we use batching and the workload partition I just mentioned. So let's see the results. So setup, we mainly use the latest consumer degree 4090, and also a server grade A100 80 gigabytes for the test and benchmark. And our baseline is mostly OpenFHE and other SOTA GPU implementations. So here's the parameter set we tested. And for the performance of NTT, we have a lot of graphs also inside our paper. And this is a table we can show around 40% of speed up compared to previous work. This is the previous work, OS 23. And for the bootstrapping performance, we mainly compared to CPU to get around more than 200 times speed up in regarding to the throughput. And we also compared with the recent another concurrent GPU acceleration work, XLK 25, and get more than 2 times speed up in some specific parameter sets and tasks. This is their paper. Also, they will talk about this paper this afternoon. So in conclusion, our Vela FHE delivers strong speed up for both schemes on GPUs, and is more than 30% faster GPU kernels versus recent GPU NTT work, and has gained more than 300 times speed up over multi-threaded CPU with over 7,000 operations per second as the throughput. Okay, that's all for my talk. And if you have further questions, we can also contact us via the email. Okay, thank you.
Questions?
Yes. So first of all, congratulations on really good results. I was wondering a bit, so your latency is exceptionally good, even compared to the throughput. And I was wondering, so is there something special you do to get that extreme latency? I did not read the paper, to be honest. But could you try to give us a sense how you got such a good latency compared to other designs?
Okay, thanks for your question. So you talk about latency, not the throughput. So do you mean that the latency is about we only use GPU to calculate just one
yeah,
operation,
exactly.
one ciphertext operation?
So coming as an FPGA designer, usually when people do FPGA designs, they either go for the full pipelining, like I prefer this approach, and then you get good throughput, but your latency suffers a little bit. In your case, you've got both. You've got very good throughput, and it seems like your latency is indeed just the inverse of the throughput. So like you do one, no pipelining, and it goes very quickly.
Yeah. In fact, we didn't use latency as our main metric in the final result. So the final result is we batch a lot of tasks together to get the high throughput. So we mostly use amortized time to describe just like you mentioned the time per ciphertext. So the latency we use is mostly about the low level arithmetics. We gain some speed up because So basically we just have a very high throughput design because GPU is more capable of that. So for the actual hardware accelerators, I think they have a way better latency. Yeah.
Okay, thanks.
Any other questions? Maybe a quick question from my side. Are you efficiently utilizing the tensor cores in the GPU? Is that how you get so much speed up?
Oh, thanks for the question. That's a nice question. So actually, we didn't utilize tensor cores.
Okay.
Because tensor cores operates on like 8-bit integers or some very small integers. So in fact, we need to implement both for 32-bit integers, also for 64-bit integers. So it's not very suitable to just like that slice the integer to 8-bit. So we didn't use tensor core. Thank you.
Okay. Let's thank Hao for the nice presentation. Request the next presenter to come to the stage.
I got it. So thanks for the introduction. So I will talk about efficient and compatible domain functional bootstrapping via subroutine folding. So first, let me just take a very quick recap of the background. So fully homomorphic encryption allows arbitrary computations on encrypted data, and all my mainstream string scheme feature noisy ciphertext. And bootstrapping is also still the only known way to refresh the noise. And after bootstrapping, the plain text remains unchanged, but the noise goes down. And functional bootstrapping is a very no bootstrapping where we not only refresh the noise, but also evaluate function at the same time. So this functionality just greatly improve the throughput of bootstrapping. So first, let me just review some about a few of TFHE bootstrapping. So the underlying ring is a power 2 cyclotomic ring. So the first step is called a procedure called blind rotation. So it puts some encoded message in the exponent of some primitive root of unity. And this is typically multiplied by some free ring element called the test vector. Because this procedure requires a series of homomorphic multiplications, so it is the main cost. And the second step is called the constant sample extraction. So if the test vector is a polynomial with all the coefficients being 1, and then the constant term of this will be either 1 or -1, depends on the most significant bit of the encoded message phi. So if we do a simple mapping, the constant extraction would actually output the encryption of the MSB of phi. So more generally, we can encode some function into the coefficients. And yeah, the constant term extraction will output the evaluation of this function if one of the following two cases happens. The first case is that the function is an acyclic. So the problem is clear because the function type is restricted. And the second case is that the encoded message lies in the first half of the domain. So, but by doing this, we cannot support modular arithmetic over the full plain text space. So, to overcome these limitations, so many works have proposed different full domain designs for evaluation of general functions. So personally, I just classify them into two categories. The first category is overcoming the acyclicity. So the first line of work in this category is selection via MSB. So recall that in acyclic bootstrapping, the result would be incorrect if the MSB of phi equals 1. So the corresponding solution would be we can homomorphically select the appropriate test vector via the MSB of phi. And many works follow this idea, but all of them require at least 2 invocations of blind rotation, and they require additional packing conversion keys, the key switching key. And the second line of work in this category is using ring extension or lookup table compression. So let me just give an example of ring extension. So if we double the FW modulus, the encoded message would lie in a half domain, but with a random MSB. So we can just use the regular bootstrapping to evaluate the MSB and then do the homomorphic subtraction. So it reduces problem to the half domain case. So we can use the regular bootstrapping to do the rest. So because the final output comes directly from the regular bootstrapping, so it has minimal noise growth. But on the other hand, so some schemes require doubling the ring degree, and all of them require 2 invocations of blind rotation, and they all require additional constraints on the input or output noise levels because of the homomorphic subtraction. And the third line of work in this category is using function decomposition. So if you write the original function we want to evaluate as a linear combination of several subfunctions, where each subfunction can be evaluated using regular bootstrapping or potentially in a recursive way. So this framework does not require extension, and it has small noise growth. So these 2 points just implies that this framework has compact bootstrapping key size. But it also algorithmically requires more blind rotations for evaluating the subfunctions. And the second category, I call it avoiding the next cyclicity. This is because the next cyclicity arises only when you consider the behavior or coefficients over power 2 cyclotomics. So circumstances change if you consider the problem from another perspective. For example, we can use circuit bootstrapping. In this example, we can homomorphically extract the bits using circuit bootstrapping, and then use a level mode of TFHE to evaluate the function. So this framework is much more efficient for high precision lookup tables. It scales nicely when the precision increases. But however, it requires the invocations of circuit bootstrapping, which is typically heavier than the regular bootstrapping, and it requires additional packing or conversion keys for the circuit bootstrapping. And the second line of work in this category is using the technique of homomorphic equality test. So if we define the equality test function like this, and then any function from d modulo 2n to z can be expressed as a z-linear combination of the equality test function. So this is a fundamental mechanism. So there's only one work using this idea, so which was inspired by the AP framework. So theoretically, this framework is attractive because it does not require ring extension. It requires only one blind rotation, and it can even work beyond power 2 cyclotomics. But however, so this framework has very large noise growth for homomorphic evaluation of the equality test. So this implies that it is quite inefficient in practice. So this is our motivation, to make this framework practically efficient. So let me just give a brief recap of our original framework proposed in TCC 2024. So in that work, we propose equality test just to use the trace sum of all the cyclotomic subfields. So this is an equality test. And let me just give a redundant illustration of how it works. So we can just homomorphically check the equality of the encrypted message with all possible input values, and then multiply the result with the corresponding output value. So if we add up all these resulting separatists, we should get the evaluation of this function. And we can see that the sign part is z-linear, and the trace in the equality test is q-linear, and that's z-linear. So we can aggregate some computations. And this is the actual framework used in the original work. So it just uses the linearity and the transitivity of the trace. So in this framework, for obtain the encryptions of subring elements, it uses automorphism evaluation and BFA multiplication. And for batch homomorphic equality test, it uses pan-test separatist multiplication and trace evaluation. So this is asymptotically efficient, but with very large noise growth. So it is inefficient in practice. So our solution is to propose a new variant of the original equality test. So the key factor we use is quite simple. It's just a relation between the trace and the constant term extraction over power 2 cyclotomics. So if we combine these two equations, we just get a new equality test that based solely on the constant sample extraction. So this is our equality test. And based on this equality test, we can build a new function evaluation formula. And based on this formula, we can try to build a workflow, a new workflow. So in this workflow, we just use additional blind rotations to get the encryptions of subring elements. And then we use sample extraction and addition to complete the evaluation of all the homomorphic equality tests. So the correctness of the workflow below is guaranteed by the formula, above formula. Okay. So here's a brief summary of the differences of techniques. So our first task is to obtain encryptions of subring elements. So we just use additional blind rotation. So this gives us small noise growth, but yeah, it comes with much more computational cost. And the second task is batch homomorphic equality test. So we just use new test vectors and sample extraction. So this gives us minimal noise growth, but we cannot support we can only support a single lookup table. This is because the test vector is initialized before the blind rotation. So now we need to solve these two problems. So this is our first further optimization. So this was inspired by the polynomial factorization strategy used in FDFB2. So our test vector, which was a ring element, can be factored like this. We can see that the second factor is independent of the function f, so it can be initialized initialized before the blind rotation in the test vector. And the first factor is dependent of the function, so we can multiply it using plain text separated multiplication after blind rotation. So this can be, we can multiply just many different functions. So this also has some further implication, and that is this test vector is equals to 0 if the subring index I is no less than log t, and t is a plain text space. So this further implies that a sum equal test or the blind rotations are unnecessary. So this finally implies that only log t blind rotations are required. And this is our second optimization. So we can work directly over the subrings. So recall that we require the encryption of the subring elements. And the first key fact is that this encryption can be produced using blind rotation over many rings. We can use the most compatible ring, we can use the full ring, and we can use all the subrings between these two rings. So the second key fact is that GRWE is generally more compact for the same security level. And this is and for the efficiency of blind rotation. So if the ring degree is somewhat large, not too small, so we can get better efficiency if we decrease the ring degree. But this is not always the case. Just to put it extremely, for example, the plain RW. If the blind rotation or plain RW is quite, the efficiency is quite low because we cannot use NTT. So we can expect there's a sweet spot somewhere in the middle. So we just stop there and use that subring instead of smaller rings. So this is our final framework and the comparison with the original framework. So we can see that in this framework, the noise growth is much smaller, and we used the rectangles to represent the scale or the cardinality of the underlying ring. So we use the width to represent the ring degree and the height to represent the size of the modulus. So we can see that in our framework, we have rectangles with that are narrower and shorter. So this is because we can use rings with smaller ring degrees and a smaller modulus. So here are some selected experimental results. So for parameter setting, we just ensure the security level to be at least 128 bit. And we set the decryption failure rate to be sufficiently small for the CPAD security. And we can see some framework level improvements over the original framework. So we can see great improvements in terms of runtime and key size. And compared to other full domain designs, also our scheme is the most efficient with full multi-threading of CPUs. And it is one of the most compact in terms of bootstrapping key size. So finally, I would like to make some concluding remarks. So here are some key features of our design. So the first one is parallel friendly. So this is because all blind rotations revolved are mutually independent. So you are free to parallelize them. And the second one is it has compatible bootstrapping key size because our noise growth is reduced. And the second one is easy to implement. This is because all building blocks has been implemented in existing libraries like OpenFFG, like TFHRS. So for implementation, there's nothing new. So we just improve the algorithm using a different algebraic perspective. So, but on the other hand, so our scheme is less efficient than some prior full domain designs in single-thread settings. Yeah, so this is our limitation. So finally, I would like to mention some potential future directions. So maybe we can explore some implementations on other platforms because it is parallel friendly. So just like for example, the GPUs just mentioned in the previous talk. And so our techniques like the homomorphic encryption test may find other applications in privacy preserving protocols. So that's all.
We have time for some questions. Maybe I'll ask a quick question. So you mentioned other privacy preserving protocols.
Yeah.
So any examples that you can think of?
So I think maybe you can use it to build some protocols like private information retrieval, maybe.
Yeah.
Maybe.
and you will probably be exploring more accelerated implementations for this.
Yes.
Any questions? Okay, let's thank Han for the excellent